let's make a deal. Welcome to this quick hits video. My name is Kevin Fiesel, and I'm the proprietor of Catalaxy Services LLC, a consulting firm which specializes in work all across the data platform space, especially SQL Server. In the prior video, I covered a concept in statistics known as Bayes' theorem. In this video, we are going to cover a particularly interesting paradox that can easily confuse the sharpest of cookies. Let's talk about this a bit more in the classroom. The year is 1975. You've just scored a ticket to the hit TV show Let's Make a Deal. You dress up in your finest horse costume and, amazingly, get selected. After a bout of shrieking and jumping, you make your way down to host Monty Hall. Monty shows you 3 doors. Behind one of the 3 doors, a brand new car. Behind another of those doors, a pretty decent toaster. And behind the final door, a goat. Now, most people wouldn't want the goat, but you don't know which door will net you a car and which will get you a goat. Armed with just the information I've given you, you decide that you want door number 2. 2 was your lucky number in college, after all, and you're feeling pretty good about it. Now, Monty tells you, hey, it's your lucky day. He is going to show you what is behind door number 1. It's the toaster. At this point, you know you either have a car or a goat. Now, it's getting pretty exciting and maybe a little tense, and Monty gives you one last chance to change your mind. Do you really want to stay with door number 2, or wouldn't you like to change to door number 3? The question is, at this point, should you switch to door number 3 or stick with your original choice of door number 2? If you think about it for a moment, this is a story about information. You start with 3 doors and no other information. Thus, there's a 1 in 3 chance that you've picked the right door. But now Monty has given us a bit of information. Door 1 was not the car. Now you have a 50-50 chance that door number 2 has a car and a 50-50 chance that door number 3 has a car. Given this, it seems that there isn't any value in changing your door, right? Well, it turns out this intuition is actually wrong. Let me explain why, and then we'll go to a demo and prove it. Let's retell this story just a little bit. Before Monty shows us what's behind door number 1, each door has a 2 in 3 chance of not hosting our car. After opening door number 1, this probability has not changed. There is still a 2 in 3 chance that door number 2 does not hold the car. But door number 3 has had its available information change because of one basic principle. Monty would never show the door with the car in it. He knows what's behind each door and makes sure to show the door with a lesser valued item. What's critical here is that we can now link door number 1 and door number 3 together. Combined, doors 1 and 3 have a 2 in 3 probability that one of the 2 will host a car. And after we open door number 1 and reveal the toaster, the combination of 2 doors still has a probability of 2 out of 3 of hosting the car, but the probability of door number 1 hosting the car is 0. Therefore, door number 3 has a 2 in 3 probability of hosting the car, and our original door number 2 still has a 1 in 3 chance of hosting that car. For this reason, it makes sense to swap, even if 2 is your favorite number. Now, this particular finding is something that is quite the paradox. Smart people intuitively rebel against the idea. Therefore, I'm not going to ask you to take this on faith alone. Instead, we are going to build a simulation and prove it. Join me in the demo as we do just that. Welcome to Visual Studio Code. I have here a fairly simple Python script. I start by importing the random library. Then I've created a function called makeADeal, which takes a number of tests or simulations. We'll perform that many simulations of the problem. We start off by keeping track of how many times our door is successful versus how many times the other door is successful. In total, I'll have 3 doors and create a set of those 3. Then, for each test, we'll follow the same basic process. We'll first choose one of the 3 doors at random. Then we'll choose the winning door at random. This could be our door, or it could be one of the other 2. At this point, we need to come up with the set of possible doors that Monty will open. Monty will never open our door, as that would ruin all of the suspense. But we also know that Monty won't open the door with the car behind it for the same reason. Therefore, the doors to open will be the set of doors except for our door and the winning door. This means that the doors to open set will contain one door if we did not choose the winner and two doors if we did choose the winner. Now we open at random one of the doors in the doors to open set. We show the person what's behind that non-winner and offer the person a choice to switch. But let's posit a very stubborn person who never changes his choice for door. We let the rest of the situation play out, opening all three doors. If we picked a winner, we iterate the my door successes variable. Otherwise, we iterate the other door successes variable. We'll do this until we hit the requisite number of tests and return these two counts. We'll then print out the success rate for my door selection, followed by that of the other door. Let's give this a run with 1,000 tests, as that will be enough to get close to the expected answer. As we run this, we can see that the numbers are approximately 1 and 3 and 2 and 3, where we get it right 1/3 of the time, but the other door was the right decision 2/3 of the time. And if we want to make this even closer to the ideal number, let's up the number of tests to 1 million. This will take slightly longer, but still finish in the time that it takes me to finish this sentence, because let's face it, this is a really simple bit of code to simulate. And with a million simulations, we're quite close to a 1 and 3 and 2 and 3 split, respectively. At the end of the day, when Monty asks if you want to switch to a different door, make the swap. You will increase your chances of success considerably. And that was the Monty Hall problem. I will admit that it took a few iterations of learning about the problem to really understand the logic behind the scenario. For years, I was one of those people who would assert that the odds became 50-50. Hopefully, this explanation helps, and you'll spend less time asserting the wrong answer like I did. We'll have links and show notes in the description below. And until we see each other in the next video, take care.